Hello everyone, in the lecture today we will learn a new topic, traverse, which is the method to establish a control network in the surveying. They will actually provide the measurements in both directions and distance. Generally, 3 surveyors are required to complete a traverse survey, including instrument operator, a head tillman, and a rear tillman. Also, we need to use 2 types of equipment to conduct the experiment. For the measurement of angle and direction, we have to use the theodolite or total station. Also, we need to use steel tape or EDM devices to conduct the distance measurement. Moreover, in the experiment, we need to define the traverse station or hub, which will be the reference points in the area with the given elevation and location. Generally, there are 3 types of the traverse surveying. The first one is open traverse, where we are given the location and directions of the initial line. And then we will apply the measurements for all the other consecutive lines. The second one is closed traverse. In this type, we are given the initial line and also the end line. Then we will do the surveying for all the lines in between. The last one is called a closed loop traverse, where we only know the initial line. And then we will apply the traverse surveying for all the other lines. Eventually, it will return back to the initial line. So it will form a loop. Let's first check the closed traverse surveying with the deflection angles. In this kind of surveying, we are given the initial line, say SR, and the end line, say it's M and N. And then we can have some measurement about the lines in between. Say we have 1, 2, 3, and 4 lines. The intermediate points would be T, U, V. And we measure the deflection angle at all these turning points. With that, we will have alpha 1, which is angle to the right, alpha 2, angle to the left, alpha 3, angle to the right, alpha 4 to the right, and eventually we have alpha 5, angle to the left. Assuming that we are given the azimuth of the line SR and all the deflection angles at the turning points, then we can estimate the azimuth of the line M to N as the azimuth of SR plus alpha 1 minus alpha 2 plus alpha 3 plus alpha 4 minus alpha 5. Basically, you can rewrite this equation into some general form, which will be the azimuth of the initial line plus the summation of all the deflection angle to the right minus the summation of all the deflection angle to the left. This one is a general formula for you to estimate the azimuth with the deflection angle. Let's see how we can get this equation. First, let's consider the two lines RT and TU. We can draw the directions of east-west and north-south. Also, we have the line of RT and line of TU. We know the deflection angle, which is alpha 2 to the left. And then for the azimuth of RT, which should be determined by the extension. And this would be the azimuth of RT. With that, we can find out the azimuth of TU. In the figure, that will be the line from the north to the line TU. So we can see that the azimuth of TU will be the azimuth of RT minus alpha 2. And this is just for the deflection angle to the left. Or we can also consider another example for the deflection angle to the right. Similarly, we can have the directions of east-west and north-south. Here we will consider another two lines, UV and VM. U, V, and VM. We can find out the deflection angle as alpha 4R. In addition, from this figure, we can identify the azimuth of UV, which is also determined by the extension, as AUV, which is shown in the figure here, and the azimuth of the line VM is shown as this one. With this, we can find that AVM equals to AUV plus alpha 4. So we apply the positive sign for the angle to the right. Now let's check how we can process the data from the deflection angle traverse. The table below shows the information collected from the field experiment and also the calculation based on the result. Basically, the part on the left is the observed data, and the part on the right is the calculated information. And we will see how to complete this calculation, especially the correction for the errors. Now let's see how we can conduct the calculation for the deflection angle traverse and estimate the error. In the experiment, we are given the true azimuth of the line SR, that is 350 degree, 30 minutes, 0 seconds. We also know the azimuth of the line MN, which is 104 degree, 42 minutes, 30 seconds. And from the experiment, we get all the deflection angle. Then we can calculate the azimuth of all the lines and also the azimuth of the line AM from the measured angles and find out the error between the estimated azimuth and the true azimuth for the line MN. First, for the calculation of the azimuths for all the lines. For the first one, that will be the line RT. It equals to the azimuth of SR plus alpha 1 as the deflection angle to the right. And ASR is 350 degree, 30 minutes, 0 second. Alpha 1 is 140 degree, 10 minutes, 0 seconds. Obviously, you can see that the summation is higher than 360 degree, but we know that for all the azimuths, it should be between 0 and 360 degree. So we need to apply this condition to the calculation and minus 360 degree. Which will give you the azimuth of the line RT as 130 degree, 40 minutes, 0 seconds. You can apply the similar procedure for the estimation of the other lines. We will have the azimuth of the line TU as 57 degree, 20 minutes. AUV is 106 degree, 50 minutes. AVM is 157 degree, 10 minutes, 0 seconds. And eventually we will have AMN equal to 104 degree, 45 minutes, 0 seconds. With the estimated azimuth of the line MN and the true azimuth, we can then find out the error. The error will be the difference between the estimated and the true values. So that is 104 degree, 45 minutes minus the true value, 104 degree, 42 minutes, 30 seconds, which is 2 minutes, 30 seconds. So that's the error we estimated for the traverse in the deflection angle. In the next step, we need to see how to correct the errors from the measurement. The correction is actually based on the error we calculated in the previous page. For the line MN, the error is 2 minutes 30 seconds, and the estimated value is higher than the true value. So we need to remove this one from the estimated azimuth. For the line SR, we are using the true azimuth, so we don't need to do any correction for it. And the correction is set as 0. Then we can see that in this measurement, there are 5 angles for us to estimate the azimuth, which means we want to apply the error evenly to all these 5 angles. So that is 2 minutes 30 seconds divided by 5, which is 30 seconds. In addition, the calculation about the azimuth is from the starting line to the end line, so the error is cumulative. And this indicates that the correction for the first line, RT, it's minus 30 seconds. For the second one, it's 2 times 30 seconds. That is 1 minute 30 seconds. 1 minute. And the third one is 1 minute 30 seconds. And the first is 2 minutes. And then we can calculate the adjusted azimuths. For SR, we don't need to do any change, which is 350 degree, 30 minutes, 0 seconds. For the second one, RT, we use the estimated value plus the correction, which will give you the value as 130 degree, 19 minutes and 30 seconds. The third one is 57 degree, 19 minutes. For UV, it's 106 degree, 48 minutes, 30 seconds. VM is 157 degree, 8 minutes, 0 seconds. And eventually we have the azimuth for the line MN as 104 degree, 42 minutes, 30 seconds, which is just the true azimuth provided by the experiment. The deflection angle can also be applied for closed loop traverse. Here let's consider one example. In this example, we know the initial line from A to B, and then we apply the traverse start from the line A to B, and we will measure the directions of BC, CD, DE, and then back to EA. For each turning point, we measure the deflection angle. With that, we can summarize all the information we will have. For the azimuth of line AB, the value is given, and also we can find out the deflection angle at all the turning points. Then we can estimate the azimuth at all the other lines. For the line ABC, we can find that the azimuth is AAB minus the deflection angle, as is the angle to the left, which will give the value as 114 degree, 21 minutes, 30 seconds. Similarly, we can find out the azimuth of CD as 16 degree, 06 minutes and 30 seconds. And also for DE, the value is 287 degree, 47 minutes, 30 seconds. In the calculation here, you will find that ACD minus the deflection angle is actually smaller than 0. In that sense, you need to add 360 degree to make sure that the azimuth is between 0 and 360 degree. For the line EA, the value is 170 degree, 5 minutes and 0 seconds. Eventually, we can re-estimate the value of the azimuth for the line AB as 228 degree, 0 minutes, 0 seconds. By comparing the estimated azimuth for the line AB and the true azimuth, we can see that the error here is 0, so we don't need to do any correction about the measurement. This table summarizes the result of the closed loop traverse as we showed in the previous page. Basically, by checking the error, we find that there's no need for us to apply any correction. In addition, for the real-world implementation, if you want to use bearing, you can always convert the azimuth to bearing based on the equation that we mentioned previously. The traverse can also be conducted based on interior angles. Now let's see one example to check the procedure of this method. First, we are given a line Q21 and a 6-side polygon 1, 2, 3, 4, 5, 6, and 1. So we are given the azimuth of the line 1 to Q, also the angle to the right, for the angle Q12, and we also measure all the interior angles alpha 1, alpha 2, alpha 6, which is shown as the angles in this figure. And it wants us to find out the azimuths of all the lines in this polygon. For the calculation, we need to find out both forward and backward azimuths of each side. For the first line, 1 to 2, the azimuth of 1, 2, which is the azimuth from point 1 to 2, is A1Q plus the angle of Q12. And then we can estimate the backward azimuth, A21, as A12 plus 180 degree. And the part to add or minus 180 degree is not fixed depending on the angle that you observed for azimuth. Then you need to find out the value of A23, which is the forward azimuth. That is A21 plus alpha 2. And you can find out the backward azimuth A32. Similarly, you can apply the same procedure for the other steps. You will find the A34 and A43 and A45 and A54 until you reach the point 1 again. The table on the right summarizes the calculation to find out the azimuths of all the sides of the polygon. Eventually, you will find out the azimuths of the line 1, 2, and also you will have the azimuths of the line 1, 2 based on the first equation, which you are using the given value of A1Q and the angle to the right of Q12. With that, you need to find out the closure error, which will be a difference between the estimated value and the true value from the given condition. And similarly, you need to apply the corrections for all the sides. Basically, you don't need to apply any correction for 1, 2 because 1, 2 is coming from the true angles. You need to apply the cumulative correction for all the 6 angles measured for the polygon. And with that, you can get the adjusted azimuths for each side. So that's the way for you to use traverse with the interior angle. Another way for you to conduct the correction is just based on the interior angles. First, we know that for the inside polygon, the summation of all the interior angles will be m-2 times 180 degree. We know the interior angle for all the 6 points in the polygon. Then we can do the summation about all the 6 angles and find out the value as 720 degree and 3 minutes. By the equation here with the 6-sided polygon, the summation of all the interior angles should be 720 degrees. So we find out the closure error is 3 minutes. And in this case, as each interior angle is measured independently, it's different from the azimuth, which is calculated based on the interior angles. So for the correction of the interior angle, we just need to apply the correction evenly for each angle. In this case, we have 6 angles and the total closure error is 3 minutes, which means the correction applied for each angle should be 3 minutes over 6, that is 30 seconds. And then by introducing the correction, you can find out the adjusted angle for all the points in the polygon. And then you can use the adjusted angle to find out the azimuth of all the sides. With that, you don't need to do any correction, and the result should perfectly match the line 1, 2 based on the true and estimated value. We can also use the angles to the right to conduct the traverse. Usually the angle to the right indicates that we will measure the angle clockwise. For example, if we consider the set of lines, start from Z, Y, and then A, R, S, T, U. We will have the angle to the right at the Y, which is alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. Then by giving the azimuth of YZ and the azimuth of TU. Here you should know that we need to consider the azimuth of YZ instead of ZY. Also, we measure all the angles to the right, that is alpha 1, alpha 2, alpha 5. With that, we can find out our equation. The azimuth of YZ plus the summation of I equal to 1 to n, where n is the total number of the angles we measured. Alpha I minus n minus 1 times 180 degree minus ATU will be 0. Here n is the number of angles to the right. And we can use this condition for the correction about the traverse by the angle to the right. The table here summarizes the calculation and the correction for the example in the previous page. In the experiment, we can get the azimuth of the line YZ and also the angles to the right. This is alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. We can then use this information and the equation in the previous page for the calculation of all the backward azimuths. And eventually we will find out the azimuth of the line TU. We are also given the value about the azimuth in the line TU, and then we can compare the estimated value and the true value, which will give you the closure error as 25 seconds. With that, we need to do the correction for the azimuth. Here we have 5 angles measured, so we need to divide the error evenly in these 5 angles. With that, we will apply 5 seconds for AY, 10 seconds for RA, 15 for SR, 20 for TS, and 25 for TU. And with that one, we can find out the corrected azimuths of all the lines. And that's the way for us to conduct the traverse with the angle to the right. We can also measure the azimuths of the sides directly for the closed loop traverse. The figure here shows one example of the azimuth traverse. For example, at the point 1, we have to measure 2 azimuths. One is for the line 1 to 2, the other one is for the line 1 to 5. So we have A12 and A15. By measuring the azimuths at all the points, we can get both forward and backward azimuths for all the sides. And then we can use this information for the estimation of the interior angle. For example, for the interior angle 1, we have alpha 1 equal to A12 minus A15, which will give it the value as 80 degrees 2 minutes. It could be applied for all the other points. And then we need to call the summation of the interior angles to check the error. We know for the summation of all the interior angles, the value should be n minus 2 times 180 degrees. By checking the errors, we can then apply the correction about the azimuths we measured for all the sides. The table here shows the data collected from the azimuth traverse. By observing the forward and backward azimuths, we are able to find out the interior angle and then determine the closure error for the entire traverse experiment. Similar to the azimuth traverse, we can use compass to measure the bearing of each side for the polygon to conduct the compass traverse. The table here shows the data from the compass traverse. We will actually measure both forward and backward bearing of each side in the polygon. And then, similarly, we will find out the closure error based on the summation of the interior angles. The last type of the survey we want to learn is a stadium traverse, where the stadium method is applied to measure the direction of the sides, the horizontal and vertical angles, which will be applied for you to measure the distance and the elevations of all the points and the size in the surveying area. This one can give us a very comprehensive control network for the surveying job in the future. So that's all about the lecture today. Thank you very much for your attention. With that, we finished the introduction about the basic concepts in traverse. In the next few lectures, we will introduce more details about the computation based on traverse.